Okay, good evening. I'm going to kick off now. We're running slightly late, and I know there's some more people who are due to come into the lecture theatre here, but we're mindful that there are people hopefully watching online. So we're going to start off now, and I guess the other people will come in partway through. So my name is Nick Burton. I'm Principal Applications Engineer with SPX Flow Technology, better known to most of you as Lightning Mixers, and I'm going to start off with a couple of thanks and a couple of apologies if I can. First of all, thanks to Tom Scanlon for the invitation and for organising the evening today. And thanks to you for turning up and those of you watching online. Hopefully I'll be able to keep you awake for the next 3/4 of an hour to an hour, something like that. And the apologies, the first one is that I'm not actually an engineer, so I feel somewhat of an imposter in this building, but I'm actually a chemist who has kind of drifted further towards engineering over the years. I guess I find it more interesting maybe than the chemistry. But in my defense, I do have 20 odd years in mixing. So most of that has been fluid mixing with Lightning mixers. I've done 2 tours of duty with Lightning now. And I also had a 5-year stint with powder processing with Keck Gardner, and that's 5 or 6 years ago. So I've been mixing for as I say 20 odd years. So hopefully I can give you a flavour of the job we do and some of the problems that we come across which may help when you're trying to specify or talk about or troubleshoot agitators. Okay, the second apology is that when I was discussing the talk with Tom, he wanted me to try and tailor it if I could towards pharmaceutical industry, because he felt there would be people in the room from that part of the business. That was actually quite difficult to do, and if I'm honest, I haven't really been able to do that because I wanted to keep the talk fairly general. I wanted to talk about general mixing principles, and when it boils down to it, most pharmaceutical applications are actually fairly straightforward from a mixing point of view. There's a couple of exceptions to that. Fermentation would certainly be one, maybe hydrogenation, which are more involved, more difficult from a mixing standpoint, but I felt they were a bit too niche, too specific for something that's supposed to be more of a general mixer talk. So I haven't been able to particularly tailor the talk to pharmaceuticals, but what I would say is at the end we're going to have a question and answer session, so feel free to ask questions which go broader than just the theme of this talk if you want. I would say most of if the process designs for pharmaceuticals are relatively straightforward, it tends to be the mechanical design, maybe the more the hygienic requirements which are special, sometimes even just the testing and documentation which is special and difficult. So as I say, feel free to broaden the discussion if you want during the Q&A session at the end. So the title of this evening's talk is A Consistent Approach to Agitator Design. I'm going to start by just going through what do we actually mean by mixer design, what's the goal we're trying to achieve when we're doing this job of designing a mixer. I'll then look back historically how we used to do things, okay? Because this new approach which Lightning introduced really just this year, it's a progression of the way we used to do things going back probably 100 years. So we're going to just look back not that far, but at how we used to design mixers in the recent past and see how that maybe needed some improvement. And then obviously we'll go on to the bulk of the talk is about the new software really that we're using, or the new approach to mixer design, which has just come on stream this year, and it kind of brings together various different ways that we used to look at things into hopefully a much more consistent way of working. The new approach is split into 2 or 3 different modules. There's the one we call market-based sizing, which is where you have a specific job that you're trying to do, a specific mixing application, which is relatively well understood in terms of design, and so we're able to apply known parameters, known ways of design to that specific job. That's obviously the best case, because if you've got that much understanding of the process, it becomes relatively easy to get a good mixer design. But we recognize that that's not always possible. So you can build up a library of different mixing applications, but with the best will in the world, you're never going to cover everything that you come across. You might only cover 50% of what I see coming across my desk on a daily basis. So we have to have a way of doing a general mixer design, even if we don't have the specific details of exactly what the process is. So we've got a couple of more general modules, if you like, within this software, and they're to do with blending and to do with solid suspension. So I'll talk a bit about those. And then at the end, I've got a worked example, and this is something that came up at the one of the launch meetings for the new design software. It was a real example which one of the guys brought to demonstrate, and it's quite nice because it shows that even something that's apparently quite simple from a mixer design standpoint, it can still catch us out, and that one caught all of us out, and we had a room full of supposed mixer experts, including me, and we all got it wrong. So it's quite instructive to work through that. And as I say, at the end, we'll have some time for questions and answers, and as I say, feel free to make those as broad or as narrow as you want. I'll do my best to answer them as I can. So in terms of designing a mixer, what's the goal? What's the thing we're trying to achieve in the job of being a mixer application engineer? You can kind of break it down into a 3-stage process. So the first thing we need to do is to understand the process. So forget the mixing for a minute and just think, what's the process that the customer's trying to achieve in his tank? And I've used the example of hydrogenation. So for example, I don't know if we have anybody from Pfizer here, but I know we have a number of mixers at Pfizer in Ringaskiddy, Lochbeg, where we've got a hydrogenation reaction occurring, and it's obviously helped along by the Lightning mixer that we've got in the tank. So in simple terms, that's an easy one. So the process requirement is hydrogenation. That's what the customer's trying to do. So you're taking most likely a pharmaceutical intermediate, and you try to react that with hydrogen to produce the next intermediate stage in the process. So once we've understood what the customer's trying to do, what's the process requirement, the next step is to understand, as a mixer designer, as a mixer supplier, how can we influence that process result using the mixer? In the example of hydrogenation, there's the obvious requirement of mass transfer from the gas phase to the liquid phase. There's probably also some heat transfer required, because these vessels may well be jacketed, or there may be a coil. So the mixer can be used to promote the heat transfer within that system. And again, in the case of the hydrogenator, you also have a solid catalyst. So you've got a metal catalyst, finely divided, but that needs to be suspended off the bottom of the tank reasonably uniformly in order to optimize the process. So we've broken down that fairly straightforward process requirement into 3 discrete jobs that we want the mixer to do. And then the third part of the process is that once we've understood what we're trying to achieve, then we have to design an optimum agitation system to do that. And I guess it's step 3 which will form the bulk of this talk this evening, because the new software, the new design program which we've introduced is really aiming at that. We know the process now. How do we design an optimum mixer to achieve that process? And you can sum it up like that. What does the process want from the mixer? That's what is always in the back of my mind as an application engineer. If I'm talking to somebody, or if I'm looking at a job on site, it's what can we do with the mixer that will improve this process or optimize this process? So if we turn the clock back a few years, let's say 5 or 10 years, because Lightning's a global organization, SPX is a global organization, we have offices around the world, and going back, I mean, you could go back before the days of easy communications, before the internet, even before phones were as easy and quick as they are now. And just the geographical location of different offices meant that people kind of developed their own ways of doing things. So we had different mixer design philosophies, different selection programs that have been developed in different parts of the world, and sometimes also developed to suit particular maybe market specialism. So, for example, in Australia, there's a big minerals processing industry, big mining industry. So most of the expertise in minerals processing would be located in Australia, and they developed their own systems that were kind of more specific to that particular market, those processes. And it was recognised 4 or 5 years ago that this wasn't really ideal, because we had different people doing different things, not easy to spread best practice to everybody. So there was a meeting held to kind of gather together all the different ways of doing things, and to try and formulate a more consistent approach that we'd use from that point on. I'm just going to break off now to just go through some standard nomenclature, because I'll be using terms that you need to understand. So just briefly, that's just a diagram of a simple top entry mixer. The speed of rotation we always denote N. The diameter of the impeller is always D, and the diameter of the tank is always T. And we'll talk about D over T as being the ratio of the impeller diameter to the tank diameter. We may also talk about Z over T being the ratio of the liquid height to the tank diameter. And those things become important when you're looking at the rules for how many mixers you need in a batch, or how many impellers you need in a batch, or how far apart the impellers need to be spaced. So we also talk about S being the spacing between impellers, C being the off-bottom distance, and COV being the coverage. And we'll, as I say, it's mainly D over T and Z over T that you need to remember if you can. So going back to the historical summary of where we were, you can break down the different design philosophies into a few general groups. So in some ways, the simplest way of designing mixers is to just assign a power per volume for a particular process. And that might range from something very small, say 5 or 10 watts per meter cubed, for, I don't know, maybe a balanced tank on a water treatment plant, or a noxic zone, something like that. Or it could be at the high end, so you might be talking about 1 kilowatts per meter cubed, going back to the hydrogenation example. And it could be anywhere in between. So you can, for each known application, you can assign an amount of power that you're going to put in for each meter cubed of process, and you leave that alone. You don't vary it. You just say that's the power per volume, and then all you need to know is the process and the volume, and you've got your mixer power. There may be some other loose rules on what type of impeller you're going to use, how big roughly is the impeller going to be. So, for example, a flocculation process, you wouldn't want to use a high shear impeller, because you don't want to break up the flocks as they form. So you'd use a low shear, high efficiency impeller to promote flow within the tank without breaking up the flocks as they form. But that's about as simple as it gets in terms of a mixer design philosophy. And then you can go a bit more sophisticated, and you can take the basic idea of a power per volume, and you can then vary that based on the actual volume that you're working with, and maybe also based on the impeller size, because we know empirically that when you scale up a process, you don't quite need constant power per volume. You can get away with a bit less. So if you do a pilot trial, say in 1 meter cubed, and then you're scaling up to 20 meter cubed, you don't need quite 20 times the power. You can get away with a bit less than that. So there's a potential modification of that basic method by varying the power per volume along those lines. And then there's a completely different way of doing things, which is to recognize that in a lot of cases, the job that you're trying to do is done not by power but by flow. So Q is the flow. So instead of looking at power per volume, we now look at flow per volume, and we say, same kind of approach as method 1. We're going to assign a certain flow per volume, a certain number of tank turnovers to doing a particular job. So you might say, for a reaction, I want 10 tank turnovers a minute. And for just a simple storage tank, I can get away with maybe half a turnover, maybe one turnover, depending on the scale. And then again, you keep that constant, and you don't worry too much about the rest of the design. You're focused on the flow. And then, of course, there's the method, which is in some ways the best and the worst. It's the guy who knows what he's doing, and he's written some notes sometime in the past, and he's squirreled them away on a post-it note or on a piece of paper in his drawer, or these days probably on his hard drive somewhere, and nobody else can get to it. And it's in some ways it's the best, because he might be the guy who knows more about this than anybody else in the world. But it's the worst because nobody else can share it. So it's possibly good as long as that guy is assigned the job of designing that mixer. But if it comes to somebody else, then they have no means of getting to that information. So we can see there are some problems with the variety of approaches that have been used. The obvious ones are, you've got inconsistency between different locations. You've even got inconsistency between different engineers, maybe in the same location. It's not easy to spread best practice from one office to another. And as I say, if the information isn't shared, it's dead easy that you lose it. So the guy who knows all there is to know about fermentation leaves or retires, and everything's in his head or on scraps of paper, it's lost to the rest of the business. So there's good reasons for wanting to have a more consistent approach. And the last one, which is kind of key to why we've done things differently now, is that it's really difficult to update a procedure based on new data. So you might have a procedure which you think's okay, but then you get some field data which suggests actually it's not okay. Maybe it's too conservative, maybe it's too optimistic, and you've had mixers that haven't done the job they were supposed to do. And the first priority is always to fix it, because you've got an installation which isn't working. So the imperative is to make the customer happy again by fixing his mixer. So that tends to take a priority. But what you really want to do then is go away and make sure that doesn't happen again. And without having a more centralized, consistent mixer design philosophy, it's quite hard to do that. So that was one of the real goals of the changes we've made, was that we could fairly quickly gather data from the field and update the procedures if necessary. And the software has been written in such a way that it's quite easy to do that. So as these things go, we had several meetings, and there was an agreement at the end of 2012 as to the general direction of how we were going to go, and which design philosophy we were going to use. And then really the next 2 years, it's just been refinement and testing and going back and iterating and changing it, and eventually you get to the point where, beginning of this year, it's all done. But I don't think any of us realised how difficult it was going to be, and how big of a task we'd taken on to try to pull together all the different threads of how people were designing mixers within the Lightning organisation and putting it into a piece of software. And I think it's fair to say that the software has ended up much more. It's a bigger piece of software than we envisaged at the start. So therefore, it's taken a long time. The coding and the refining and the going back and testing and then refining again, that's taken a lot longer than maybe people imagine. But it's as I say, it was launched at the beginning of this year, and we're finally at the point where we're now using it in anger, and it's turning out to be, I guess, as good as we'd hoped it would be. And as I said just a minute ago, it's been written with the idea in mind of being able to firstly add modules. So we haven't got everything in that we'd like to have in. There are other modules which are still being written at the moment, and the way the software has been written, it's going to be quite easy to fit those into the system. And the other thing, as I say, it's a lot easier to update the equation, if you like, with new data when we get it from the field. Okay, so the equation I've just put on the board is really the heart of the new design procedure. That's it. And it's got some Greek letters in which put some people off, but it's actually pretty simple. So I'll go through it and we'll be referring back to the sort of three basic design philosophies that we mentioned at the start. So you'll see we've got a base power per volume, and that's defined per application code. So that power per volume, as we said before, will be different. It could be very different for different processes, and it's defined at 1 meter cubed of volume, and it's defined at a specific impeller size, so a specific D over T, which would normally be 0.3. Which is a fairly sort of standard impeller size. It could be different. Some applications have a different standard D over T just because that's more common for a particular process. But the point is it's defined at a volume of 1 meter cubed and at a particular impeller size. Now we then vary that base power per volume based on a couple of things. So we scale on volume, but that volume is raised to a power alpha, or in fact alpha 1, alpha 2. Alpha 2 is normally 1, so ignore that for now, but the scale factor is raised to the power alpha, and as we said before, you don't quite need constant power per volume for scale up, so alpha is less than 1, and that defines how much power you need as you scale up. Alpha 2 is normally 1. Occasionally, if you have very big tanks, there's a recognition that at very large volume, the scale up can be a bit further away from constant power per volume, if you like. So that exponent we allow to come a bit smaller at very big volume. So in that case, we have an alpha 1, and then we have another alpha 2, which will kick in, let's say, above 500 meter cubed or above some predetermined volume. So that takes care of the scale factor. Okay, we then have the second scale-up term, if you like, or the second modification term, which is based on impeller size. So we said that the base power per volume was at a D over T of, let's say, 0.3. The beta factor recognizes that as you make the impeller bigger, you can achieve the same process result with less power. And this comes from the basic power and flow equations which are associated with any mixer. So you can do the same job with a small impeller running fast or a big impeller running slow. But when you work through the maths of the power and flow equations, the big impeller running slow will do that job at less power. So there's a recognition in that beta factor. So beta is negative. Okay, so as you make the D over T bigger, as you make the impeller bigger, the power per volume that you need to do the job is coming down. We then have a rheology factor, which in most cases probably isn't required. But if you have a case where there's a variation in the viscosity of the product that you're talking about, it may be that a thicker material is going to need more power than a thinner material. So really, all we're doing there is having a different base power per volume. But it's dealt with in this equation as a rheology factor, which, as I say, is dependent on the viscosity of the stuff that you're mixing. And then the SG is just a straight multiplier on power. So it's the specific gravity of the liquid, or if it's a slurry, it'll be the SG of the slurry itself, of the solids and liquids together. Now we may have some other constraints other than just the straight power per volume. So depending on what we're trying to do, we probably have a range of acceptable D over T, a range of acceptable impeller size. In normal terms, you would say your impeller wants to fall somewhere between 20% and 60% of the tank diameter. So the swept diameter of the impeller between D over T of between 0.2 and 0.6, maybe 0.65. Depending on the rheology, you might want to vary that. So if you have a very viscous material, you don't want a small impeller. So you might narrow that acceptable range of D over T, and you might go, say, up to 0.4 at the low end and up to 0.6 at the top end. So depending on the exact process that you're trying to achieve, and depending on the rheology, that D over T range can vary. And then you might want to have some rules about the spacing and about the off bottom and about the liquid coverage. And again, that comes largely from the rheology. So if you're mixing a tank of water with a modern high efficiency axial flow impeller, you can get away with positioning that impeller a long way off the bottom of the tank, and you can, if you've more than one impeller, you can have them maybe 3 diameters apart, and it'll mix perfectly well. As soon as you start increasing viscosity, you have to be more careful about where you put the impellers relative to the bottom of the tank, relative to the surface, and relative to each other. So as the viscosity goes up, all those spacing rules are going to force your impellers to get closer together, closer to the bottom, closer to the surface. And this has come out of a lot of lab testing at the lab in Rochester in the States. I was over there back end of last year, and I spent a couple of days in the lab doing some of this work, and it was quite instructive, even for me. I've been doing it for years, but it's still instructive to see in the lab exactly what happens at different viscosities with different impellers running at different speeds and different sizes. We gathered a lot of data, and basically it's that data that's gone into the software to set up the spacing rules which we're now using. I alluded to this before, so the choice of impeller will sometimes be forced. So the system won't let you choose an impeller which is inappropriate for what you're trying to do. So the example I gave before, flocculation, it won't let you choose a high shear impeller because we know that that's not appropriate for that particular process. I'm just going to briefly show you how the thing works in terms of workflow through the system. So this is what I would see as an application engineer trying to do the job, and it's pretty straightforward. The thing works the same regardless of which module you're in. So if you're doing market-based sizing or blending or solid suspension, the thing kind of looks the same, and it's fairly logical. So you start off, we put in the tank details, okay, dimensions, working volume of the tank, and one of the nice things is you get a sketch to show you what the mixer looks like all the way through. So that changes as you change different parameters, and it's quite a nice reality check. So it's not just the computer saying, yeah, that's what I want. You can actually see it and say, well, does that look sensible or not? And often you can look at a sketch and say, well, I know that's not going to work. I don't need the computer to tell me that, it just looks wrong. So it's quite nice to have that feature as you're going along. Then when you put the tank details in, tank dimensions, you then put the process information, and as I say, you're choosing at this point whether you know enough about the job to say it's a well-defined process, a well-defined application, in which case you use the market-based sizing. More general, are you going to be using the blending module or the solid suspension module? And it's asking you for obvious stuff like specific gravity, viscosity, temperature, pressure, etc. You input that data on one screen. And then the last step, if you like, is the filter, and that's really where you're constraining the search. So you're asking it maybe to look for a particular range of mixers because that's what you feel is most appropriate, or maybe there's existing mixers of the same type on site. It's at this point where you decide, is it an open tank or is there a mechanical seal? So what's the mixer going to physically be built like? It's also this point where you decide how many impellers and what type of impeller, and the software will guide you in the right direction. It won't tell you exactly what you have to choose, but it will kind of lead you in the right direction. So as we said before, based on the rheology, there are spacing rules, there are rules on impeller diameter. So it will push you to select the right number of impellers, and in some cases the right type of impeller to do the job that you're trying to do. And then basically you hit the compute button and it spits out a matrix of possible solutions, and that's important. So there's not just one right answer. There's several different answers, and it presents them in a way that you can hopefully fairly quickly home in on the one you want. And the way the software works is it will look at the range of acceptable impeller sizes, and it will start at the bottom, let's say a DVT of 0.25, and it will finish at the maximum, let's say 0.5 or 0.45, whatever the range it's specified. So if you look down that table, you'll see that it starts with the smaller impeller at the top. So the top line will be a relatively small impeller running fast, and the bottom line will be a bigger impeller. Now we've reached the top end of the acceptable range of impeller sizes. So you'll now have a bigger impeller running slow. So typically you'll see the higher power units at the top and the lower power units at the bottom. And we've got, towards the right-hand side, we've got a couple of columns labeled P and M, and that stands for process and mechanical. So the software is checking the process, and by that I mean, is the power, the correct amount of power based on the equation which we saw? And then also, are all the spacing rules met? So have we got the right off-bottom distance? Are we within range on the coverage and the impeller spacing based on the rheology, etc.? And then the mechanical column is also carrying out mechanical checks. So the things you need to worry about mechanically for a mixer are critical speed, bending moment, maybe deflection at the seal if there's a mechanical seal, maybe blade stress, depending on the physical size of the impellers, etc. So it's running maybe, I guess for each of those columns, it's probably running a dozen, maybe 15 different checks. And what you're looking for is a green tick. If you get a green tick, that means that all of those checks on the process and the mechanical have been met. So that design is good both for the process and when you switch it on, it's not going to break. Okay, so the job then of the application engineer is to decide, well, which of those half dozen, 6 or 8 selections is the best one for this process. And it's still, you still need a certain amount of experience and human intervention, I guess, to pick the best mixer. But basically all of those will do the job, and they will do the job well. So as I say, the ticks and the crosses tell you whether you've passed process and mechanical design. You can actually interrogate the thing to see what it's failed on. So if you click on the red cross against the mechanical design, it will tell you, for example, you've exceeded the limit on critical speed, or on the process side, you might have your impellers are spaced too far apart, so the flow from one won't reach the one below, etc. So I mean that's useful. So even if you've got a design which fails, it's useful as an engineer to be able to see why has it failed. Maybe I can do something to fix it. So in the case of the spacing rules, maybe if you introduce another impeller or move the impellers closer together, you'll get that to pass. For critical speed, maybe you can just shorten the shaft a bit. Okay, so maybe it doesn't need to be 5 meters long. Maybe 4.8 will be good enough, and then all of a sudden, yeah, great, you find it's now okay, and you can go ahead and you've got a good design. As I said, there's not just one answer, and this is always the case. If you give the same job to 2 different application engineers, you'll more than likely come up with 2 different answers. The aim, I guess, of the new software is to make sure those answers are pretty close together. In the past, you might have had more variability, more variation. Now we have the ability that pretty much everybody should be working to the same set of rules, which have been kind of gathered together as being best practice from all the different people who are doing this in different parts of the world. So we said we have 3 basic modules to look at. There's the market-based stuff, then there's the blending and the solid suspension. The market-based is the place to start, because if you have something which is well enough understood that it's found its way onto this list, that's without doubt going to give you the best design. Okay, so you're picking from, it's a 2-stage process. You're picking a basic field, if you like, a basic set of applications, and then within that, so we've highlighted biofarm here, then within that category there might be 10, 15, 20 subdivisions. So you're now homing in on a specific application, a specific process that you're trying to do in this tank. And once you've picked that, that's what defines the base power per volume. So going back to the equation which I showed a while ago, picking one of those specific applications will define that power per volume, whether it's 10 watts per meter cubed or 300 or a kilowatt, whatever it is, that defines the process power that you need. And that's great if you've got that level of detail, but probably only 50% of the stuff I see coming across my desk can I actually look at it and say, yeah, okay, I know exactly what that is. I can pick it and we can do the job. I would say probably half you can't do that. So we have another couple of modules which are what I call the generic blending and solid suspension. And the blending one is the one you use if it's not well defined enough that you can use the market-based sizing, but you judge that the primary requirement of the process is blending of fluids, okay? And you'll see what I mean when we come to the solid suspension. So if you've got a basic blending job that falls outside of the well-defined stuff, you would pick this category. So instead of choosing a specific application, you're now determining a level of agitation. And you get some help in doing that. And once you've decided what level of agitation you're looking for, exactly the same way as the market codes, that will define what's the base power per volume. And it may also determine the other constraints in terms of impeller size and spacing and all the rest of it based on the rheology. So I say you get some help. You get to choose from anything from storage up to violent blending, and you get some hints as to what that might mean. So for example, for storage, you're really just talking about absolute bare minimum motion in the tank. So it is a storage tank, it's nothing more than that. The surface may hardly be moving at all. You don't want to be blending different components with different properties of SG or viscosity. You're basically talking about maybe homogenizing two streams which are coming in from a process, and maybe there's some variability in SG, but only a small amount, and you just want to homogenize the two streams and hold it as a storage tank. No more than that. Moving up a bit, you get to something that we call medium moderate blending, and in this case you can cope with more disparity between the different components. So you can have an SG difference up to 0.3, and you can have a viscosity ratio of 1,000 to 1. So that's getting to be a more general purpose mixer. It's certainly more than a storage tank. You'd use it for dissolving of easy to wet, easy to dissolve solids, for example. And then you can move up again, and when you get to the top of the scale, you're up to violent blending, and it's the kind of level that you'd expect in a reactor, for example. And now you've got a wide range of component properties to choose from. So you can blend with an SG difference of 0.7 and with a viscosity ratio up to 30,000 to 1. So now you're doing some serious mixing in this vessel. And as I say, it's a judgment call as to where you pick it, but there's some guidance as to what would be appropriate for a particular job. Then there's another general module, which is the solid suspension one. That's the one that you'd pick again if you can't find an actual application within the list, but you judge that the primary requirement is solid suspension. So the blending is now less important, and the thing that's driving the design, the thing that you're going to hang the design on is suspending solids. And for that, you need to know the size of the solids, the density of the solids, and the percentage of the solids in the tank in the first place. And what we use is the Sharma procedure, which is the one that Lightning's used for many years. It's been modified a bit based on the latest lab data, but it's still the same kind of process that we've used, the same kind of procedure that we've used for a number of years. It will handle off-bottom suspension and uniform suspension. I'll just mention a bit about that, because we often see a requirement from a customer which says, I need to uniformly suspend these solids in the tank. And you look at what they're doing, and you look at the layout of the plant and the vessel, and you think, well, you probably don't need to uniformly suspend the solids, because you've got a tank with a bottom outlet, let's say, and a pump, and it's going on to the downstream process. And yes, there's some solids in there, but all you really need to do, probably, is to make sure they're suspended off the bottom. What you don't want to happen is to block the pump. Okay, so as long as you can keep the pump suction clear of solids, then that's probably job done as far as the mix is concerned. The time you need uniform suspension, and it's quite rare, is if you have a weir overflow at the top of a tank, and you might have a cascade of 3 or 4 tanks, either gravity fed or pumped. But you've got an outlet at the top. So if your outlet's at the top, not the bottom, then you probably do need uniform suspension or something like uniform suspension. Otherwise, the bigger solids, because there's always a distribution of solids, right? So the fine stuff will get taken over no problem. What you'll be left with is the big solids, the heavy solids. And if you don't suspend them far enough up the tank to go over the weir or out of the top outlet, then at some point you're going to have to shut down and dig them out. So those are the cases where you need uniform suspension. Most times you don't. And what a lot of people don't realize is that there's a big cost in terms of power and money to go from off bottom to uniform. So typically for a top entry mixer, you're probably looking at between 2 and 4 times the power to go from off bottom suspension to uniform suspension. So if somebody asks for uniform suspension, the first question I ask is, are you sure that's what you need? Because it's going to cost you a lot of money to do that. So as well as choosing between off bottom and uniform, the procedure is also able to handle free settling and hindered settling cases, by which I mean, I guess in theory, a free settling slurry is just one particle in the liquid, because as soon as you introduce a second particle, those two particles have the opportunity to potentially interfere with each other as they're settling. The reality is, once you get, you can probably go to 30-40%, and you would still consider the slurry as being free settling. But when your concentration goes much higher than that, you've then got a case where the particles are going to interfere with each other as they settle. And once you get, it depends on the exact nature of the slurry, but once you get sort of 50-60% and higher, you now have a fully hindered situation where none of the particles are free to settle as they would if there was only one particle. And what you end up with is a slurry which behaves more like a viscous fluid than a set of discrete particles in water or in liquid. And at that point, things get a bit more interesting from a mixing point of view, because now you're not worrying so much about the solid suspension and the energy you need to put in to suspend the particles off the bottom. You're worried more about the rheology, the viscosity of the thing, and keeping everything turning, and your power requirement may now start to increase. One feature of the Sharma procedure, which I'm just going to mention because it's kind of counterintuitive, is that the concept of an optimum impeller size, or an optimum D over T. And what I'm showing you there is 3 different CFD plots, which if you're familiar with CFD, it's not what you're used to seeing. It's not the velocity profile, it's the energy dissipation. And that shows you where the energy that you're putting in, it's showing you where that's actually dissipated within the tank. And if you start from the left-hand side with a small impeller, you can see that the red is the high end, obviously. So there's a lot going on in the bottom, immediately under the impeller, which you'd think would be good from the point of view of suspending solids, and it is. But there's not much happening up the wall, and there's not much happening in the corner. So the reality is, if the impeller's too small, you'll tend to get fillets building up in the corner, and the suspension won't be as good as it is if it's more optimum. The middle picture shows the optimum situation, where you've got a nice red patch on the bottom and also up the wall. So that will give you good suspension, good vertical velocity up the wall, no filleting in the corner. If you go the other way and you make the impeller too big, like the right-hand picture, you can then see there's really nothing going on the bottom. So your solids there will be settling on the bottom. These 3 CFDs are all shown at equal power. Okay, so we've got different size impellers, but running at equal power. So it's not to say you can't do the job with a big impeller or a small impeller, but it'll cost you more power. So you could get a similar kind of picture to the middle one, but you'd be turning the wick up in either case, either too small or too big. It's not as good as it is if you get the D over T right. Okay, I'm going to finish with, as I said, a worked example, and this is something that came out of the launch meeting that we held a couple of months ago when we first introduced this new software to the some of the guys out in the field who were going to be using it. Okay, and we had a bunch of people from Europe who came to our office in Didsbury, and we had 2 or 3 days of training and meetings. And when we sent out the invitations, we asked people to bring with them examples of mixer inquiries that they'd seen in the recent past, so that we could kind of do a live test of the software, so we could demonstrate how to use it, and also they got the idea that we hadn't just set up examples that were artificial and we knew they were going to work. We wanted people to see it working live on one of their own real problems, so that they got confidence that the system was actually pretty good. And this was a nice example that one of the guys from, I think it was Holland, brought with him. And it's nice because on the face of it, that looks about as easy as it gets in terms of mixer design, because mixers are designed to do blending, and this is just a simple blending of 2 things. You've got a tanker with some water in. I think it was 5 meter cubed of water that you were starting with, and you're adding an additive at 9,500 centipoise, so relatively thick, and you're adding that to the water, and you finish up with a finished product which is about 7,500 centipoise. You've got a 25 meter cube vessel, and that looks, as I say, about as simple as it gets. So if the software is any good, it should be able to eat this for breakfast. And what we did was, well, okay, I think it was something to do with adhesives, but it wasn't anything that we could find a specific application code for. So we went to the general blending program, and we said, well, okay, it's easy. We just have to pick the correct level of agitation based on the rheology and the SG of the 2 components that we had. The SG, as it happens, was almost 1-to-1. I think it was water to start with, and the additive was either water-like or maybe just under on the SG. So the design was going to be driven by the ratio of the viscosities between those 2. Obviously, water's 1 centipoise, and the additive was 9,500 centipoise. So we've immediately got a viscosity ratio of 9,500 to 1. So based on the description of the various levels of agitation, you have to pick vigorous blending, because otherwise your viscosity ratio isn't met. Okay, so that's good for 10,000 to 1. We've got less than that, so that should be okay. SG difference is no problem. So again, that looks to be the way to go. At that viscosity, the spacing rules built into the system with the Z over T, the liquid height to diameter, tell you that you need either 2 impellers or 3 impellers. And again, that's probably what you'd expect as just looking at it as an experienced engineer. You'd be expecting 2 or 3 impellers in that tank. And sure enough, you hit the button and you get a number of valid solutions. So on the face of it, the systems work really well, and we've come away with a good solution, and we can pick one of the ones with the green ticks, and there's your design. But the problem was, in a room full of people who were experienced in mixing, and we probably had over 100 years experience between us in that room, we all looked at that and thought, no, it's wrong. It just felt wrong. It felt like it was too big of a mixer. It's 25 meter cubed, and it's giving you 30 kilowatts on the motor, and it just felt wrong. And a 70, for those familiar with Lightning gearbox designations, a 76 size gearbox is a big mixer, and we all felt you should be able to do that job with a smaller mixer and less power. Now, as it happens, we've come to the point in the day when it was lunchtime, so we didn't really have time to talk about it too much. So we had to stop and go away and have lunch. And then over lunch, the penny suddenly dropped. That we realised, there's a few of us realised what we'd done wrong, and we went back and revisited the thing after lunch, and we interrogated it a bit further. So I'm going to go back to one of the first slides I showed, which was, what's the goal of designing a mixer? What is it we're trying to do? And this is what we said. So the first thing you have to do is understand the process requirements. Then think about how can the mixer interfere with that process? How can it improve that process? And then step 3 is what the software should be doing for us, which is designing the optimum system. So assuming the software is working, we haven't failed at step 3, but I think we've failed at step 1. And one thing I always say to people, if you're looking at a mixing application, is the understanding the process requirements is often helped if you think about the thing from start to finish. So if you have a batch process, start with an empty tank, finish with an empty tank, and think about everything that happens in between. And that's, I think, what we failed to do in this example. And that's why, although the software gave us the right answer for the inputs we'd put in, I think we fell at the first hurdle. So let's go back and revisit that same example, doing what we should have done first, which is thinking about the batch from start to finish. So at the start of that batch, I think it was 5 or 6 meter cubed of water that was going into the tank, and then you start the flow of the additive, and the first drop of that high viscosity additive hits the water. Okay, so let's think about what we've got there. Well, as we said, the viscosity ratio is clearly 9,500 to 1 because that's the additive, and we know water's 1 centipoise, so that's fine. But at that point, the bulk viscosity is only 1 centipoise because it's just water with 1 drop of additive. So we'd previously said 7,500 centipoise, and it wasn't. It's actually only 1 centipoise. And another thing, we haven't got 25 meter cubed. We've only got 5 meter cubed. So in 2 cases, we've been highly conservative in what we thought we were designing on. That's the first drop. Then you go to the end of the batch and you say, okay, what happens with the last drop of additive? So now we really have got 25 meter cubed of product in the tank, plus this last drop of additive going in. And we really have got a bulk viscosity of 7,500 centipoise because that's the final viscosity. But now look at the viscosity ratio. It's not 9,500 to 1. It's not even 2 to 1. It's 7,500 in the bulk, and it's 9,000 in this last drop of additive. So again, we've been too conservative in the design. So the original assumption, we jumped the gun because we didn't think about the batch carefully enough. We missed something really quite obvious that all of us should have spotted. As I say, there was loads of experience in the room, and I put my hand up. I missed it. So did everybody else. And it was instructive because it appeared to be such a simple process. We've looked at the start and the end of the batch. I think we should probably consider that they might not be the worst case. So you could have an intermediate situation where there's an appreciable volume in the tank and there's an appreciable viscosity difference. So it might be too optimistic to only consider the first drop or the last drop. So you could go and run 5 or 10 different cases if you had the time, but I think for the purposes of we just want to mix a design, let's not over egg it. So let's just take a guess and say 25 meter cube volume, 7,500 bulk viscosity, and let's pick a viscosity ratio not as high as we had, but certainly more than the situation right at the end. So let's pick 1,000 to 1, okay, which still feels conservative to me, to be honest. By dropping the requirement for ratio from 10,000 to 1,000, we're now dropping from vigorous blending to medium blending on our scale. So obviously that means that the power is going to come down because the choice of level of agitation determines the base power per volume in the equation, which is then modified based on volume, etc. So we're going to drop the power. And in this case, when you hit the compute button, what you now end up with is a mixer which is significantly smaller than we had before. So we've now dropped from a 76 size to a 74, which is a much more reasonable, sensible size of mixer for that tank. That now feels about right. And the motor power has dropped significantly. Instead of 30 kilowatts, we've now got 18.5 kilowatts. And again, that now feels about right. So yeah, hopefully by thinking about it a bit more carefully, even the experts can eventually get it right. And hopefully over the last however long I've been talking, I've given you some insight into how we design mixers, and hopefully we'll get maybe some sympathy when we start asking lots of awkward questions when we're asked to look at mixer design. And I know it's difficult because you send an inquiry out to a supplier, and it's annoying when you get back a load of questions. But sometimes the questions are important. We try and pitch it so that we don't overburden you with more information that we need. But I hope that last example shown you that actually sometimes the more information we have in terms of the process that you're trying to do, the more likely it is that we'll get to the optimum design in the end. And speaking of questions, we've got some time, I think, at the end for questions and answers. So as I said at the start, if anybody wants to go wider than just the subject I've been talking about, I can't guarantee to know the answer, but I'll certainly do my best.
Will it handle both cases, CSTR and batch?
Yes, it will. Yeah. So it depends on the process. I mean, there are some modules certainly within the market-based sizing where it's really designed around a continuous process. So I'm thinking of like a continuous neutralization, flash mixing in the waste and water industry. It's at that point and once you specify a continuous process, it's then asking for more information. So it will ask you for the retention time or for the flow rate, and at that point. So take the neutralization example. It's then the retention time which will drive the base power per volume. So if you have a short retention time, it will increase the power compared with a longer retention time.
Does it give any statistics as to the extent of mixing, like liquid deviations or anything like that?
It doesn't, but there's an assumption within the software of what we mean by a well mixed batch. So there's other things you can do if that's important. So this software is really designed to give you the answer, or give you a selection of possible solutions that you can look at. If you then want to go deeper and maybe do some calculations on blend time, for example, or on, I don't know, heat transfer coefficient, you wouldn't do that within this piece of software, but you would take the solution that this has suggested, and you'd then run a separate calculation to give you the blend time or the heat transfer coefficient, and then you can maybe go back in and modify that mixer. Yeah.
Staying with CSTR for a moment, and this is probably outside of the bounds of the model. Are there any rules of thumbs as to the persistence of the plume between the influent and the exhaust pipe?
Not really, but you would want to be. It will certainly be suggesting that you want to avoid bypassing. So it will tell you. It will ask once you've specified continuous. It asks you where's the input and the output, and it's really just making sure you've thought about it. So I don't believe it takes into account the fact that you have the possibility for bypassing, because it assumes that as a reasonable application engineer, you know to avoid that. So if you're going in at the top, you want to be going out at the bottom, and vice versa. And you may need to put baffle plates in to try to avoid bypassing.
Would you be on the CSTR example, if you have a bottom outlet, you don't have a uniform suspension, then you can have a smaller agitator?
Yeah, absolutely. I mean, as I said, it's a common, I don't know, mistake. It's a common misconception that people imagine they want uniform suspension when they probably don't need it. So as I say, it's always worth investigating. If somebody's telling you they want uniform suspension, they may be right, but it's well worth everybody's time just to investigate that a bit further, because as I say, there's a big penalty. There's a 3-4 times power penalty.
You may have to, when you're designing the tank, think ahead to the agitator.
Yeah, and that's something that we're always really keen to get involved in. Too often, by the time we see the inquiry, the tank's specified, and it's the wrong shape for a mixer. And sometimes there are good reasons for having a tall tank. If you're trying to run with a big turndown ratio of batch volumes, let's say you want to you've got a 10 meter cube tank, but you also want to make batches at 2 meter cube. Sometimes in a stirred reactor, the only way you can do that is by having a tall tank, so that you've got an appreciable liquid level over the bottom impeller at low volume. And that's okay, but I think often we see a tank and it's not an ideal shape for mixing, and there's no good reason for it. It's just that, as you say, nobody's thought about the mixer. So we're always keen to get involved as early as we can. And we'll sometimes be asked to specify tank dimensions. So I had a job last week where the customer says it's 5 meter cubed. You tell me what the tank dimensions, and that's ideal. If we're in at that point, it's great. We can always work with something that's not ideal, but of course it's better if we get to specify. And the simple reason why a roughly square batch is better, so roughly 1-to-1 in terms of liquid level to diameter, it's better because you can get away with fewer impellers. So in most cases with a 1-to-1 batch, you probably only need one impeller unless there's an appreciable viscosity. And it makes the mechanical design easier because a tall tank needs a long shaft. And a long shaft, once you start to worry about critical speed and bending moment, you've either got to have a steady bearing in the bottom of the tank, which most people don't like, or you've probably got to over-design the mixer. And that means you might be going from a 50mm shaft to a 75mm shaft. And then, by the way, the gearbox you've chosen for torque, it won't take a 75mm shaft, so you have to go to the next gearbox size up. So everything starts to escalate, and you can quickly find you've doubled the price of the mixer compared with what it would have been if you'd had a more appropriate batch geometry. Yeah.
I think on slide 14, you might just comment on running cost versus capital cost for different options that you have.
So you're talking about big impeller running slow versus
for the selection.
Small impeller. Yeah, so you'll end up with a range of possible mixers which will all do the job, and you'll typically have a small impeller running fast with a high power and a big impeller running slow with a lower power. And as Martin says, there's an analysis to be done of capital cost, which will mostly come down to the amount of torque you're putting in, because the gearbox is a big part of the cost of the mixer. So capital cost versus running cost, and clearly the big motor, the high power motor, is going to have more running cost in terms of kilowatts of electricity. But that might also be the lower torque design. So you can have a situation where you've got to choose: am I going to spend a bit more now to have a benefit in terms of total running cost over a 10-year design life or whatever it is? And because you have a range of possible solutions to choose from, it does allow you to think about these things, and that's one very good reason why you might not choose the lowest cost mixer in the first place, because you actually want to think about the life cycle cost of running the plant. And there may be other reasons. You may want to choose a particular mixer because it's got a right angle gearbox rather than a vertical motor, and you've got headroom problems. Or you may have a site where there's half a dozen of a particular size of gearbox already, and you want to try and minimize the spares holding. So there's any number of reasons why you might choose one or other mixer, but the point is you've hopefully got 3, 4, half a dozen to choose from. So it does allow you to play tunes on exactly which one you're going to choose. Yeah.
In a neutralization tank where you've got a single impeller, you've got a choice. You can either have the central plume going down or the central plume going up. I had a case a few years ago where the customer wanted to have the central plume going down, so you just dump in his acid or base at the center. And I pointed out, well, look, in that case, it's like you're like trying to balance a pencil. It's fine as long as the agitator stays central. Once it goes off center at all, the force of the agitator is going to try and bend it more. My concern at the time was that, well, if the central plume was going up, the agitator was trying to bury itself in the liquid and trying to self-center. And a few years later, the shaft bent. I suppose my question is, seeing this issue actually playing out, if you did have a situation where you had the central plume rising, i.e. the agitator is trying to pull itself into the tank, where would you inject the chemicals? The customer didn't want to be injecting strong acid or sulfuric at the top, where it was going to be essentially pushed back up.
Yeah, I mean, what we normally recommend is that you inject on the suction side of the impeller within the swept diameter. That's which will be difficult. I mean, I guess an alternative would maybe be in the upstream up at the wall so what you're trying to do is incorporate the additive within the loop. So with a single down pumping impeller in the middle of the tank, assuming it's a baffle tank, what you're trying to do is achieve a top to bottom single loop flow pattern. So I would say best practice in terms of additives is at the top into the suction side of the impeller. If that's not an option, then I guess maybe somewhere in the strong upflow section would kind of give you the same thing, because it would be rapidly incorporated into that loop. But it's interesting talking about the main flow impinging on the impeller and bending the shaft, because that's something that we do try and avoid. It's normally coming in at the side. So in something like a flash mixer or a neutralization tank, you've normally got the flow coming in from the side and going out the other side. Hopefully,
in this case, the recirculation is probably higher than the flows, and they probably do something daft like running the impeller at the liquid level as well.
That doesn't help. No, certainly, and it doesn't help unless if you haven't designed for it. I mean, that's something that when we get into the mechanical design, there are different cases. So there's the case, and normally a continuous process is the best case. Okay, because the liquid level's not varying, so you don't have to worry about the worst case situation where the liquid level's rising or falling through the impeller, which we know is a multiplier on the fluid force. So we have to design for that. If you've got a continuous liquid level, you can pretty much guarantee that unless it's run out of spec, you can guarantee that the impeller's always fully covered with liquid. So that's an easier mechanical design. But it's possible if the mixer was designed expecting that to be the situation, but actually the level was lower and the impeller was close to the liquid surface, that could cause problems. What I was going to say about the side flow is that situation normally would have the main flow coming in at the side, and what we try and avoid is the situation where the impeller is at the same level as that inlet pipe, because we know that can cause problems with an additional sideways force on the shaft.
Do we have any more questions? So, I know we've run here just happening, so just thanks very much for coming over and giving such an informative presentation. I think it's been a very good discussion, and hopefully at some future stage we'll get an opportunity to carry it out again. This event has been webcast, so it will be available for future viewing should you want to look back on it. I'd also like to thank Martin for organising Nick to come over. There's complimentary refreshments afterwards in the bar, so if any questions, I'm sure you
I'll be in the bar, so just feel free to ask any questions you want.
So thanks very much, Nick.
That's right, thank you.